Let's talk about a hybrid problem we're going to use to diagnosis. Here's our symptoms and codes. The vehicle always runs on the internal combustion engine, or the ICE. It doesn't use the electric traction motor. Now look at the codes we have to support this. We know this condition can happen if the battery state of charge is too low or if the temperature is too high. But our first example, P0A7D, the high voltage battery state of charge is low, tends to give us an idea of why we're not using the electric traction motor. P1435, charge and discharge balance problem. The PCM, the controller, does not like the way the system is charging and discharging. They're not in balance. We'll have to see what's causing that. P1446, individual battery module voltage deviation. It's looking at the individual battery blocks and there's differences in voltage. So from this, we know we're going to have to diagnose the high voltage battery pack. We will want to do it without exposing technicians to the high voltage dangers. So let's go look at this. But before we start jumping in and tearing things apart and putting on rubber suits, let's make sure we get maximum use of scan data. Now let's review scan data a little bit. We're going to need to know what's available in scan data to diagnose this problem, and we'll quickly cover the basics and review this area, and then we're going to use it to pinpoint the exact area that's causing the problem. And then we found that it's necessary we may have to do a few extra diagnostic steps to be totally accurate in our diagnosis. Just to review, a block has 6 cells. It takes 2 of them to make. A brick has 6 cells. It takes 2 of them to make a block. They're connected in series to produce as much as 330 volts DC at 200 amps is what the fuse is for. They don't normally put out 200. That's the max. So the max in this case is 66,000 watts. We say that just to make you pay attention. It's going to show us blocks of 2 cells, 15 volts per block. We've talked about that. We've seen scan data. We know it has to be between 50 and 68, and we know that about 38% it's going to stop using heavy battery loads like the traction motor, and we know that 80% is going to stop using regenerative braking. We know they paired them up in pairs of blocks. This is the highest reading block and the lowest reading block. We're going to see that later in actual scan data. We know we've got to have a temperature. The traction motor is going to shut down at 138. We've got to make sure we're not anywhere near there. We know we're expecting between 288 and 300 volts. This is normal. And we're going to go and talk about how we got that number. We got it by multiplying 240 cells, 40 bricks, 20 blocks, 6 bricks per block, 12 bricks, 6 bricks per brick, 12 bricks per block, whatever you want to count it. It's 240. Here's our 2 numbers we came up with. And we have normal current flow. We're also looking for that aspect of it. Now here's our problem scan data from our problem vehicle. It's on the left, and the data on the right is our typical data. So right off the bat, you see we have 25.8% state of charge, almost half what it was in a normal battery. Now this is low enough, it will shut down the traction motor. That's the first finding. That supports it. The first block we look at is 15.3. That's pretty close to what we expect in normal, maybe 0.2 high. Then the minimum block is 465. This cell can exert excessive heat and damage the battery if that's true to the value. And as we look down at temperature, it's in a normal range. We said that if we multiply our 240 cells by 1.2, we get 288 volts. Well, if you remember also, we told you that 0.9 volts is the lowest we want to see any individual cell go. If we multiply 240 times 0.9, 216 is the lowest possible reading we want. And looking down here, so once we see this voltage is too low, we need to go to the next step and look at individual cells. Now, this is the block 1 through 8. We have a small screen here. We can't get them all on there. Let's start down through them. 15, right where we expect it to be. 15.3, that's maximum variation. We've covered the maximum allowable variation we'll see in the battery. But what these 2 values tell us is that at some point in time, recently, this battery has been charged. So that means we should have a normal state of charge if all batteries are in the same condition. But right away we can see 14.6, that's too low, 14.5, 14.3, 7.47, much too low, 9.56, 9.14. We've got something major going on. Let's scroll down and look on down the line here. 10, 12.1, 11, 14.65, 12, 9.22. Scroll down some more, and we've got enough. But what we have found here, we found the 4.65 we're looking at. We found our maximum. We found our minimum. We're at 15.3 was our maximum. 14.65 was our minimum. So ScanData has captured this information for us. We now have determined for sure we have an uneven charge of the battery pack. Now that means something has gone wrong. We're going to have to go in and find out what. But this has taken us this far without ever removing it. Now the reason for taking the extra time here is this is going to be a lot of man hours. It's going to take extra time. Now we need to see what this is going to look like when we remove the batteries. After you have this big battery pack out, how do you test it? Well, let's stop and look at this. We're going to use some test equipment from Midtronics. It's a baby version of some of their hybrid test equipment, the GRX 1200. But we're going to use a handheld in this particular case because we can look at individual cells and get some additional testing. Now, you could use a voltmeter to measure each battery pack, but you already know they're low from ScanData. Is there more conclusive testing than just voltage testing? Because if we use voltage as our only test criteria, we'll fail good cells, and we may miss some bad ones. The Midtronic test equipment measures voltage, but it also goes on and measures mhos, or conductance. Conductance is also measured in Siemens, which is another way of calculating conductance. Here's our printout from a handheld unit we use that was made for testing large banks of batteries. And we'll start down through it. Remember, we're now down to bricks. We're looking for 7.5 volts. We're out of the case. We're down to one brick at a time. So we start off 7.558. That's pretty close to what we expect to see. Looking down, we see a bunch of 7.5s all the way down till we get to this one, which is lower than 7.5. Then it's almost close to 7.5. Then a bunch that are below 7.5. All the way down here to 2.517. But look down a little further. Here's one that's 8.4 volts. And down a little further is two others, 7.7 and 8.1 volts. Looking at this, we would condemn a whole bunch of batteries if we were going to do this. But we have one extra measurement. We can look at conductance. At the same time, the Midtronics measured the voltage. It also calculated conductance. Now, what do we have about conductance? Well, it's measured in mhos, and it's the opposite of ohms. How conductive is the battery? To have good conductance, I must have active electrolyte and two good electrodes. If they're good and the electrolyte's active, I will have good conductance. Now, in this particular case, it's measuring the ability of the electrolyte to conduct ions between the electrodes and the electrode's activity itself. It's the inverse of ohms. In our readout, it's going to be in mhos. Now, Doc and Bill spec for now is a minimum of 100 mhos. This is still in the research phase. We've only seen a few bad batteries. We don't have enough. We've seen a lot of good ones, but we don't have enough marginal ones to tell you what the magic number is. But we know below 100, they're bad. So now let's go back up here and start down mhos. In the first row here, we go from 130 to 138. And then we get to some that are much lower charge. Now, lower charge batteries will have slightly lower mhos, but they won't be so bad they will fail. But we do have one down here that's 100. But when we get down a little further, we got a 66 and a 57. Now, we can't tell you whether that 100 is good or bad, but we can tell you that the 66 and 57 are dead batteries. They're the two batteries causing most of this problem. Well, how could two batteries cause this problem? Well, the problem is these two batteries leaked electrolyte, and this is the result. Have you ever tried to fix a flashlight after an alkaline battery leak? Most people tell you to throw it away. What we have to do now is all this copper has to be thrown away, and we get new shiny pieces, and we've got to neutralize all the acid in the batteries. Remember, corrosion causes poor contacts to the batteries and to the sense leads. Where this is excessive, we've probably had poor contact and couldn't read the voltage was present, and it doesn't connect from battery to battery properly. So while it may have been charging good at one time, once this went bad, we're pretty sure the charging came to a pretty sudden halt. We've got to get it back to where it looks normal like this, and we've got to get it all cleaned up. Look at the level of corrosion we're talking about. We're trying to make these connections. We've got to have clean ones like the top, not the bad one at the bottom. Just to put this in perspective, this is the size of what you're looking at right here. They're not just giant, big pieces. That's close-up photography. To correct the problem, we had to clean everything up and put the batteries and put all new hardware in, and then start putting the batteries back together with no spilled electrolyte. But there's a next generation tester we'll tell you about. It can measure conductance of the blocks without removing the battery pack. This is a big new thing. It's the future you're going to go to sometime down the road. The simple diagnostics with this tester is really amazing. We're going to do a full throttle accelerate to 25 miles an hour as fast as we can get there, and then stop as quickly as we can. This puts the battery through full load doing acceleration, where we run the ice and the traction together, and then we go into regenerative braking and charge the battery. You get a printout of each battery block for acceleration, conductance, and voltage, along with a set for deceleration. The results are in Siemens because we've got to calculate the difference, so don't confuse it with Mohs, but it's going to give us the same results. But before we look at conductance and understand what's happening, we need to see what happens to voltage as the high voltage goes through its periods of heavy loads and high charge currents. This is something you can do in scan data as well. We're going to start off by looking when the battery is providing power to the traction motor, the current readings be positive in a range of around 100 to 170 amps. No, it doesn't go to 200. That's the fusing. And doing regenerative braking, current readings are negative and range around minus 90 to minus 110 amps. This indicates the battery is putting current, or the system is putting current back into the battery. Now, don't confuse this with an alternator. An alternator normally puts out current flow, so anytime it's normal, we measure it as positive. The electric motor normally draws current flow. So anytime it's drawing current flow as a motor, it's positive. When we turn it around and put it back in the battery, we now call it negative. It's just a little terminology that might get confusing, so don't let it catch you. Let's go look at the information. We have recorded a test drive, and we're going to talk about this test drive and get down to details. First at the top, we've picked where the yellow cursor's lined up with the trace. The engine speed is at 1,248. Now, if you want to read it, it's right over here to the left. This is the reading where the yellow cursor is. At the time we're doing that, now let's look at the slope of that RPM line. It's increasing sharply. If it's increasing sharply, we must be accelerating. Now notice that this battery pack current flow going to the high voltage battery, or going to the traction motor, is running 107 amps. It's going up just like we were going up when we were doing the acceleration. This is positive current flow. We now have the ICE and the traction motor running together. So the engine and the motor are both putting out power. It gives us better acceleration. Now, anytime we draw 100 amps out of a battery, voltage is going to drop slightly. We've been looking at 14.9 to 15.1. But once we go to supplying loads and start charging, we've said before that the voltage would be above and below the ideal. So right here at this spot, we're at 14.45 volts. Now this in itself is a test. It's telling us how far the battery voltage increases and how far it decreases. So this is taking care of one aspect, current draw when we're in acceleration. This time, the slope is coming down. We're in decel. We make quick decels because we put on the brake. We're running 992 RPM. Current flow is minus 97.4 amps. We're charging the battery at 97 amps. And the battery pack voltage, when we're charging it, has risen to 18.14. Let's put this in perspective. That puts the battery voltage at 362.8 if we multiply it by our 40 blocks. What was 300 sitting at idle, or sitting with the engine off, is now 363 volts approximately when we're charging the battery. So you do see these cell voltages go up and down. But let's put this in perspective. During regenerative braking, we generated 35,242 watts of power. 35,000 watts of power being generated right here, with tremendously large numbers. This is energy that would have been wasted as friction material. So this is the part of the deceleration is coming from this electric motor acting as a generator and working real hard. And the rest is coming from friction. We'll go into that more in detail later. Then we slowly go out here and we go coasting along at cruise. And we told you at cruise, we'll run on the ice and the electric motor will be just idling along doing nothing. So here we've got 2,080 RPM from the internal combustion engine. The current flow for the traction motor is 2.6 amps. It's not being driven. This is called zero torque miles. It just has enough current flow to keep it turning. And you'll see when we get to the power splitter that the motor generator has to turn all the time. So this is just simply telling us we're turning at zero current, zero torque. The bottom, 16.2, says we're being recharged. And this means that the internal combustion engine is recharging through motor generator 1. We can go back and start doing now and do the same test, only getting results here. You're going to see the same type of results. High voltage when we're charging, low voltage when we're using it as a load.